Okay, today we're going to be covering kinetic energy. Kinetic energy and the work energy theorem. Work energy theorem. Okay, we learned from work that our work is really the dot product of our force and our displacement vector. In fact, that should be a delta right there. Okay, work is force times delta R. Okay, but we can take this is the more simplistic version of it, and it's really the integral of this. So it's really work equals the integral of our force dot dr. And a way that we can talk about kinetic energy is that this is really just a way of storing energy. It's the storage of energy in the motion of an object. In the motion of an object. Okay, can you guys read that okay? Or is that getting pretty small? Yeah, reading okay? Alright. Alright, so we're of course going to draw a demonstration of this, and what better way to draw a demonstration of this than to draw a crate? Because that's what we do. We physicists, we love our crates. Love crates. I love crates. I love crate. Crate, crate, crate. Love the crate. Alright. So, here's our surface. And here is my crate. As soon as I get my... Alright, and then here's a crate, and it's on wheels. And... Alright, there's my crate. Okay, we exert a force on the crate. We exert a force F on the crate. The crate has mass M. Okay, when we exert a force on the crate, we give it a velocity. In fact, we're going to give it an initial velocity. It has an initial velocity, and we still exert a force on the crate. Okay, the crate will go from... That's hard to see. Okay, the cart will move a distance x. Okay, it moves a distance x. Okay, one of the cool things about doing this digitally is that I don't have to redraw diagrams. And we continue to exert a force on this. But now, after it has traveled a distance x, we've pushed this cart for a certain distance x with a certain force F. We now have a new velocity, v. That's v, and that's the new v, and it is longer because we have imparted energy that is stored in the motion of the object. All right, how much work did we do? Well, we know that our work equals our force, okay, but times our displacement. Now we know that this really right here, this is the, let's go draw in there. This is actually the net force, right? That's the net force on this thing, not just the horizontal force. We just drew it horizontally. So make sure of that. And this is good, but what does our force equal? Our net force is actually equal to what, according to Newton's second law? Not a rhetorical question. Force equals mass times acceleration. So we could rewrite this as mass times acceleration times our displacement. Okay, now, this does, of course, assume a constant force right now. Okay, that the force is not changing. The force can change, and if it is a variable force, then we will derive the more general term using calculus, but we're not there yet. Okay, so we also have, okay, you may remember, we're gonna plug in for right here a different version of acceleration. We're gonna take our kinematic equation, v squared equals v naught squared plus 2a delta x, right? And you guys might see where this is going here. Okay, and we're going to solve this for our acceleration. All right, so we're going to get a v squared minus v naught squared divided by 2 delta x is going to equal our acceleration. Yeah? That make sense? Okay, so then we take this acceleration, we're going to plug it right back in here. So, okay, we are now going to perform a magical transformation with the snap of my fingers. Ta-da!
Wait, what happened?
Ah. Okay, another miracle of modern technology, I am able to shrink the size of what I just wrote so I have more room on the rest of the page. Ah, for those of us that don't plan out accordingly. Okay, so, we want to express work. We want to express work in terms of its velocity change. So, what does this look like? Well, this becomes, okay, so what effect does the force have on the motion of the energy? Well, our work then, okay, our work is going to equal our mass times this component down here, times our acceleration, v squared minus v naught squared over 2 delta x delta x. Yeah? Okay. Well, our delta x's are going to go away. All right, they disappear. And we wind up with, okay, but we still have this 2 down here. So we're going to wind up with our work equaling 1/2 mv squared minus 1/2 mv naught squared. But what is 1/2 mv squared? 1/2 mv squared is our formula for kinetic energy. So what this really winds up being is our final kinetic energy minus our initial kinetic energy. And whenever we subtract anything that is the final minus the initial, that's really just what symbol? Okay, it's our delta. So this is our delta K. It's our change in kinetic energy. Now, if we start at 0, if we start at rest, okay, then work just winds up being our kinetic energy. If we start something from rest and we get it moving, then it will, whatever work we've done becomes its value of kinetic energy. So this is a conservative, assuming it's a conservative force that we're pushing this with. But this is the idea of the work energy theorem. Okay, in fact, work equals delta K is a law of nature. Okay, just like doing the procedure. No, doing the procedure is not a law of nature. It's just a law of my classroom. But in this world, it might as well be a law of nature. This is an actual law of the entire universe. That the amount of work the amount of work that goes into a system is equal to the change in the kinetic energy of that system. Okay. So, in fact, the idea, and yes, I'm actually going to spend the time to write this out. Okay, the work done by a net force will be equal to the change in kinetic energy. Okay, this is the work energy theorem. Okay, and it's kind of a big deal. Okay, this is a colossally important. It's not quite as important as F equals ma. Okay, but it is a colossally important concept. All right. Now we can go on from there, and just for rigor's sake, our work does equal the integral of F net dot dr. Okay, and this equals the integral of mass times acceleration dot dr. Okay, but in this particular case, the work is going to equal the integral of mass times acceleration dot dx. Okay, and this is if we have a variable, if we have a variable force acting on this. That's going to become mdv dt dx. You guys follow me here? Okay, our acceleration, right? Our acceleration is going to equal dv dt, right? But we still have this dx term over here. Yeah? Alright. Well, this then, we can move this around, and we're going to swap places with our dv and our dx. Alright, so we can write this as m dx dt dv. Well, what's dx dt? Our dx dt is just velocity again, right? So this becomes equals mv dv, and now you guys may be seeing where we're going with this. Okay, mv dv, so work equals, we factor out the m, integral of v dv, which equals m v squared over 2 from v naught to v final, and here we get the same thing where it's 1/2 mv final squared minus 1/2 mv naught squared, and that's the more rigorous proof of our work energy theorem, that it's really, our work is the change in our kinetic energy. Okay, for any kind of variable force as well. Okay, this is our first form of energy that actually has an equation. Okay, if you throw, now think about this, throw a ball. Okay, so we'll take a, oh look, because I'm a physics teacher, I have a ball sitting on my desk. Okay, so who's ready to catch this? Okay, it's a baseball, so I don't think I should throw it at Corey because I can't trust him to not bounce it off into Ahmed. So Anybody else want to catch this? Okay, Emily, I'll start because Emily's in a safe area, and I trust Emily's hands more than I trust Corey. Okay, so we throw a ball. It's a force times a distance. So, but where is this coming from? This is all in my throw, right? I'm going to exert a force as long as I'm in contact with the ball, and the distance is as long as I'm actually imparting a force on the ball. So you ready? Yeah. All right. Oh, sorry. Okay, I totally undershot. Emily, that's my bad. Okay, so the energy that it had when it left my hand is equal to the force times the distance that it left my hand. Okay, now, once I throw the ball, it has the ability to take that energy that I have put into it and turn it into work whenever it hits something. In fact, the exact same amount of work that Emily did to stop the ball, okay, is the same as the work that I put into the ball. Okay, there was a change in kinetic energy, and so if I do work to give it a positive change in kinetic energy, she will have to do negative work to take that kinetic energy away. Either way, it is a work kinetic energy equivalence there. Yeah? Okay, that you take from one bucket, pour into the other bucket. All right. That is all, but now, kinetic energy, because there's that v squared term in there, it's always positive. Okay, whenever an object, it's for our intents and purposes here, in Newton's universe, it's impossible to be moving slower than not moving. Yeah? Now, I think there's some new quantum stuff where there's actually negative movement, but I don't want to get into that right now, and it's not going to do us any good to study it. However, yeah, I know, it's freaky stuff, so I don't even want to blow, it blows my own mind, let alone you minuscule high school students' minds. However, kinetic energy itself, the value of kinetic energy is always positive. However, work can be negative because you can have a positive change or a negative change in your kinetic energy. So please don't get that confused. Your kinetic energy the amount of kinetic energy can change. Okay, and it can change in the negative. So delta K can be negative, but K by itself, the value of K is not. And that is it for the work energy theorem.